I reported here the number of errors and also the elapsed time. Oh, it turns out it's faster than that. It was only 10 seconds per epoch and 95 total seconds to get down to 338 errors. Oh, looks like I got even lower here. You see how it got better and better and better and better, and then it actually danced around and didn't get better for a while? Why does that happen, do you think? Yeah, if we go back to, I don't have that picture anymore. Just imagine the line bouncing around in the bottom of that bowl. It can't really get any better because it's down at the bottom. That's sort of what's happening. So yeah, 1.5 minutes is all it took me to do that. If yours is slower, I'm okay with that. This isn't a class about performance or optimization or coding practices or things like that. It is kind of about optimization, but not that kind of optimization. But it shouldn't take you a half hour, right? 1.5 minutes isn't a big deal, especially for neural networks. They usually take much longer. Okay. I put here a list of the layer sizes that I used. I went from 784 to 80. Now, let me point out, each image is 28 by 28 pixels. So 784 is the total number of pixels in this image. So there should be 784 inputs into your neural network. I mapped to 80, then I ran that through a nonlinear layer. Notice the nonlinear layer has 0 weights because there's nothing to tune. Tan H is just tan H, has no parameters. Okay. Then another linear layer that went from 80 to 30, then a nonlinear layer, then another linear layer that went from 30 to 10. Why 10 outputs? Because I used a one-hot representation, so I was predicting 10 values, which could be interpreted as the probability of each digit, and then I found the maximum one, and then compared that with the test labels, and determined whether they were correct. Does that make sense? Great. Okay. I want to do some current events real fast, then we'll get into the meat of this discussion today. I just happen to be poking around here. In the wake of fake news, several universities, including MIT and Harvard, introduced new course on ethics and regulation of AI. Have you seen a lot of fear lately that AI is going to take over the world and therefore we better teach students how to make ethical decisions regarding AI? I've seen a lot of that. I'll tell you what I fear much, much more than AI is having stupid people in charge. And the more we teach ethics and the more we try to regulate what AI is supposed to do and what AI is not supposed to do, the more we're giving somebody the power to decide what our computers should and should not do. And somebody is going to use that power to decide computers shouldn't do anything that jeopardizes my next campaign, or computers shouldn't do anything, that's a little different from what they originally intended, which is don't kill off humanity. So I usually oppose these things. I go so far as to say, I hope robots do kill off humanity because then we'll be better off. Obviously, I'm joking. I don't think robots should kill off humanity, but I don't know. It always bothers me when legislators seem to think that they can understand our technology better than the researchers and need to tell us what to do with it. How do you guys feel about that? Anybody want to comment on there? Okay. Well,
third party look at your stuff.
It is. I'm very glad there's regulation regarding, say, nuclear weapons. And, maybe AI is going to be a dangerous thing. I don't know. But I have a hard time. If it ends up actually being intelligent, I fear that people are going to go to a blood-based right system as opposed to a merit-based or intelligent-based right system. So lots to think about there. And thus, there's my version of ethics. Yeah, okay, better move on. Here's something else I noticed. Bill Gates, this is highly relevant to the previous article, warns tech companies that they're inviting government intervention by spurning government intervention. Basically, a bunch of tech companies are not giving the government backdoors to their cryptography, and Bill Gates is saying, hey, you better watch out. If you keep telling them no, they're going to raise an iron fist and pass laws. So now we find ourselves in an interesting situation. Let's suppose you agree with me that the government shouldn't regulate AI. Then what? Maybe actually spurning that's the wrong thing to do, because then they'll come back and say, oh, yes, we will. So now how do you play the game? I don't know. It's complicated. But I have planted the seed in your mind to start thinking about these ethical issues. Okay. Amazon is designing custom AI chips for Alexa. What does that mean? I don't know. I haven't even read the article. I shouldn't even present this to you. But usually what that means is they're putting a neural network on a chip. The reason they do that is as fast as computers are. Remember, it took me 1.5 minutes to train on MNIST. Wouldn't it be cool if we could do that in 10 seconds instead? Turns out neural networks on hardware are a lot faster than neural nets in software. And so that's a big thing. Maybe there's a lot of overlap if you're a computer engineering major, or maybe you'll find that understanding them in software will be really important, even if in the future you're working with them on hardware, just so you know what's actually going on. Ironically, the first neural networks were done on hardware, not on software. So we're kind of coming full circle. You'll find in technology there's always patterns like that. Remember mainframes and dumb terminals? You're like, no, that was the 70s, Dr. Gashler. That was before I was born. Well, that was a thing back then. Now we call it cloud computing, but it's really just the same thing. It's dumb terminals where all the computation's really done at a centralized server. It goes in cycles, and we're going to spiral around many times. And AI is going to so far away that by the time we actually get there, we will have passed this, oh no, it's going to kill us, no, it's not, many, many times. Okay.
With Google's like TPUs that everybody knows about, how does that compare to like what other companies are doing? They even have their own things, do you know?
I really don't know. I'm not a hardware guy. I kind of work in the software and the theory land, so while I'm loosely aware of its existence, I haven't really gotten so far as to get down into the nitty-gritty details of it. I usually even, pretty much all of my colleagues are doing lots of work on GPUs, and that's great that it's super fast and optimized for them, but I usually work so far in theory land that I'm just happy if it even works, and my time, I think, is more valuable than the computers, so if I can come get something working in a few weeks, I don't care if it has to run for 2 months to yield results. Now, that's kind of a bad attitude. GPUs are giving huge speed ups in neural nets these days. And yes, I have written GPU optimized versions of it, but every time I keep changing it, it's such a pain to update the GPU version. And so, I don't know, long story short, there's a lot of work to do to make hardware and software all come together, and we're still trying to figure out intelligence. So, I don't know. Here we go. Countries that are most highly invested in automation. What does automation have to do with AI? Well, basically, if you add AI, you can take out the human, right? Which means automation, to some extent. Apparently, South Korea is the top, then Singapore, then Germany, Japan, Sweden, Denmark, and finally, United States. Don't know what that means, but we're far enough up on the list that it looks like there's a career in this stuff if you're interested. Okay. There, I did some current events. Let's talk about, I started drawing a neural net here. I'm going to draw a very simple neural net so I can keep my math simple. Suppose we feed in x, that's a tiny x, and we get out y with a hat.
5 layered
I'm going to call this, let's see.
That's linear.
It depends where we stick parameters. Let's put a W1 here. We'll put a W2 there, and I'll just have it output a Y. So this isn't actually linear. This is just an identity pass straight through arrow, or a non-existent arrow, if you will. And so I'll call this a 4-layer neural net. Now, classically, we considered the nonlinearity and the linear weights to be 1 layer altogether. So some people might call this a 2-layer neural net. I like to call it a 4-layer neural net. Okay, so given this neural net, and this is a really lame one because you would never want to pass through just one unit, right? All that's going to do is stretch and bend this, the values in X. You can't really do much with that. We would usually want a whole array of neurons in both of these layers, and that way it could do all kinds of interesting transformations to our data. But for the sake of keeping the math simple, suppose this is what we have, and we want to derive stochastic gradient descent. Can we do that? First of all, let's write out the equation for just this neural network. Now I'm going to, let's see, kind of like that picture to be up here. So let's keep that there and move this to there and see if that works for us. Okay. I'm going to say hat y is equal to the, here, let me LaTeXify that. Come on. There we go. Is equal to the hyperbolic tangent of, and then how about bias 2 plus weight 2 times the hyperbolic tangent of bias 1 plus weight 1 times x. And I'll LaTeXify that. Is that the correct equation for this neural network? Interesting how the picture goes left to right and math seems to go the opposite direction, isn't it? Okay, but basically y is the hyperbolic tangent of, because I picked tan h for my activation function, because again, it doesn't matter. Bias plus weights times what feeds into it. And what feeds into it is the hyperbolic tangent of bias plus weights times x. So do you agree that's the function for this thing? Okay. Now what we want to do is differentiate let's try to figure out how we can update W1. So I'm going to take the partial derivative with respect to W1 of the sum squared error. In other words, if we ask the question, if I were to change W1, how would that change the sum squared error? The answer to that question would be this gradient, which would be exactly what we need to know how should we change W1. Well, we want to reduce sum squared error, right? So that is going to be equal to, whoops. Now we've done this before, but we've not done it with a nonlinearity, and so I just want to show you how that works out, and then you will have great understanding of all the math involved here. If we take the partial derivative of sum squared error, how do we express that? Sum I of y sub I minus hat y sub I squared. Pretty much like that. That's sum squared error, right? Now, remember I have this whole equation that computes y hat. So I could just plug that in for that y hat, right? Unfortunately, I erased it, so I'm going to have to type that all out again. But that's going to be sum of I. I'll LaTeXify this in pieces so I can copy and paste later. Y sub I minus, and then I need to stick that equation in there, which is going to be tan h of b2 plus w2 times tan h of b1 plus w1 times x. And that should be subscripted. LaTeXify that thing. And is that going to work? Okay, and this part too. There, I've turned that into an equation. Is this the same thing? You understand why? Great. Now let's differentiate it. How how do I take this thing and push it out of there? What do I do with calculus next? I can already do it for this step, right? I can just take this summation, put it right there. Isn't that a fair step? Because that summation doesn't do anything. It's just going to be the sum of all the partial derivatives of that thing. Great. Next, let's take this, and what else can we do? I claim we could actually, no we can't. We're going to have to take this stuff, and that's going to be equal to 2 times let's see, I can copy all the way up to here. Didn't work. It can be 2 times all of that times the partial derivative of the inside, which is going to be, again, all of that. Okay. This is the kind of math that really smart people are always up there doing on a white chalkboard, and you know their hair's sticking up like this, and they talk with a German accent, and you know they're crazy because nobody can write an equation that long and understand what it means, right? How does it feel to be one of those? Doesn't this feel cool? You totally get it, don't you? Okay. I mean, really all it is, hey look, we had this 2 and we pulled down the 2, and then we're multiplying by the derivative of the inside. But it made this crazy big long equation that we actually still are comprehending, except I forgot a parenthesis right there. Okay. Is there one? Oh, you're right. Okay. When you find an error in an equation that big, you know you're feeling awesome. Okay, so last time I was eating at Macaroni Grill, they give you paper covering on your table so you can write with crayons on it. I always like to derive back propagation on my counter just so that some random person picking up my plate says, whoa, some smart person ate here. Makes me feel good. Yes, it's vain. I'm a weird duck. Okay. But do you see where we got this equation? It shouldn't be that bad. It's really just the equation for the output of the neural network. And notice that we've pushed the derivative all the way down to here. We don't even have to worry about anything over here because, hey, it's just math and that's what computers do, right? So all we got to do is get this derivative out of this part of the equation and then we're done. Then we've got an equation for the gradient of the whole thing. As scary as it looks, I hope this doesn't scare you. Okay, how are we going to get that derivative out of there? What's the derivative of tan h? Anybody know?